Hello friends and welcome to my channel again. Today we'll be discussing a problem in complex analysis. This is a very important problem and it was asked in NET, CSIR NET, possibly 2016 or 17. I don't remember the exact year. For the previous all problems, you can visit the following website. The link is given in the description. So without any delay, let's see the problem. Consider the polynomial fz, which is z square plus az plus p to the 11, where a is an integer which is non-zero and p is greater than equals to 13 is a prime number. Now suppose that this a square is less than equals to 4 times p to the 11, then which of the following statements is true? F has a 0 on the imaginary axis. F has a 0 for which the real and imaginary parts are equal. F has distinct roots and F has exactly one root. So you have given a polynomial and we want to analyze the roots. Okay. So since this is a quadratic polynomial, analyzing the roots will be helpful if we analyze the discriminant of this polynomial. Okay. So this is a hint. You pause the video, try for a solution, and then watch the solution. Okay. Okay. So I hope you tried for a solution. As I told, in order to solve this problem, we will analyze the discriminant. So recall that if you have a quadratic equation ax square plus bx plus c, then what is the uh, discriminant of this? So the discriminant, which we wrote as d, is equals to b square minus 4ac. Okay, so this is the discriminant of this polynomial. So here you have your a is 1, b is a, and c is this. So what is the discriminant? B square. So second, a square minus 4 into the coefficient of z square times the constant term. That is 4p to the 11. And that is what I have written here. The discriminant of the polynomial is given by this. Now we know that if d is bigger than 0, then real roots and distinct roots. If d is equals to 0, equal, and d is less than 0, then imaginary. Okay, so these are the things that we know. Okay, so let's analyze that what is the discriminant of this polynomial. And we have in the problem, you recall that we have given the condition that a square is less than 4 into p to the power 11. So it means that this quantity a square minus 4 p to the power 11, since this condition is given, so this implies this quantity is less than equals to 0. So d is greater than 0 is not possible. So it means that this does not have purely real roots. Okay, fine. So now you see that it's less than 0. So it means that there are two possibilities. It's either equals to 0 or it's either less than 0. So since this is easier, so let's analyze what if it equals to 0. Okay. So see, if a square minus 4 to p to the power 11 is 0, then what is a square? A square is 4 times p to the 11. From here, if I found out what is a, so a is square root plus minus square root 4 p to the power 11. And then what is a? So I can write this as 2 times p to the power 5 times square root of p. Okay, so this is my a. Now what is p? P is a prime number. So square root p is a irrational number. Okay, so square root p must be an irrational number. Now what is a? A is an integer and this is an integer. and this is an irrational number. So a must be an irrational number from this fact, and which is a contradiction because a is an integer, and hence a square minus 4p to the power 11 cannot be equal to 0, and therefore the polynomial cannot have equal roots. Okay, is this clear? Okay, let's think it through and we proceed. So therefore what we analyze that a square is less than 4p to the 11. Fine. So then what we can conclude from this that the roots of this quadratic equation will be distinct and imaginary. I'm not saying it's purely imaginary. I'm just saying it's imaginary. Okay. So hence, what was option D and C? Let's see. So the option C was f has distinct roots. This is correct. And f has exactly one real root. This is false. Okay. So now we are left with the two options. F has a 0 on the imaginary axis and f has a 0 for which the real and imaginary parts are equal. So let's analyze each option. The first is f has a 0 on the imaginary axis. So this we can solve by two methods. The first method I'll describe now, and the second method which will be described when we'll solve for option B. Okay. So see, f has a 0 on the imaginary axis. It means what? It means that z equals to alpha I. So this will be a root. This will be a root. Okay? Because see, imaginary axis means this is the real and this is imaginary. So f as a root means it will be something here, here, something like here. So it's like, so it's alpha times I form will be there. Okay. So now what was the equation? Equation z square plus az plus p to the 11. If I'll put z equals to alpha I, what will I be getting? Alpha I to the square plus a times alpha I plus p to the 11. What is this? I square is minus 1. So this is alpha square minus alpha square plus a alpha I plus p to the 11. And this is equals to 0. But you see, because y equals to 0, because I'm assuming that alpha is a root. But what is this? See, this is a 0, this is a complex number. So it means that alpha square equals to p to the 11 and a alpha equals to 0. Can it be possible? No, because alpha square cannot be that p to the 11, that we don't know. It can happen, but a alpha is equals to 0. This cannot happen. Why? Because a is non-equals to 0 and alpha is a pure imaginary root, so that means alpha is not equals to 0. So this thing cannot be possible, and therefore f cannot have a 0 on the imaginary axis. So this option is also false. Okay, very easy. Okay, let's see the next option, the option B. F has a 0 for which the real and imaginary parts are equal. Okay, so what are the roots? The roots are, so roots of a quadratic equation, just recall that a square plus bx plus c equals to 0. So roots are minus b plus minus square root d by 2a. Okay, and here what was the quadratic equation? It was z square plus az plus p to the 11 equals to 0. So minus b, that's minus b, plus minus a square minus 4p to the 11 by 2. Okay, but we know that this is negative. Okay, so this we can write, I can just take minus as common. So square root minus 1 is I. So that's why I've written minus a plus minus I times 4p to the 11 minus a square. Okay, so here I have taken like this, I can write minus of a square, minus of 4p to the 11 minus a square. Okay, and then I have taken minus 1 as square root as out. Okay, fine. Now if I'll write it as a real and imaginary part, what we are getting? It's minus a by 2 plus minus 4p to the 11 minus a square by 2. Now, is this 0? No, this is not 0 because a is not equals to 0. And hence from this also, we can see that it cannot have a 0 on the imaginary axis because this is non-zero. Okay, so this is again a justification for option A not to be true. Okay, so option B, if option B is correct, let's say the option B is what? F is 0 for which real and imaginary parts are equal. So if option B is correct, then what will happen? This quantity is equals to this quantity because this is a so this is I, so this will be I, sorry. Yeah. So this is the real part and this is the imaginary part. So if option B will be correct, then real and imaginary parts will be equal. Okay. So it means that this equals to this, squaring both sides, what will be given? A square 2 will be cancelled. A square equals to 4p to the 11 minus a square. Just pull this a square, I'll be getting 2a square equals to 4p to the 11. A square equals to 2p to the 11 and hence a equals to plus minus a square root 2p to the 11, which is equals to a square root plus minus square root 2p. This. Okay. Now, this is an integer, non-zero integer, and this is an irrational number. Why? Because, see, of course, p is greater than equals to 13, but that is not needed. Even p is greater than equals to 3 is fine here. Okay. Because if p is 2, then this can be possible. Okay. So p has to be greater than equals to 3 is sufficient. Okay. But p is greater than equals to 13. So fine. So this means this is an irrational number. So this is a contradiction. And hence option B cannot be true. And therefore, f has a 0 on the imaginary axis. This is false. F has a 0 for which the real and imaginary parts are equal. This is false. F has a distinct root. This is true. And f has exactly one real root. This is also false. So why I have analyzed all the options? Because this was asked in part C and where more than one options can be true. If it would have been asked in option part B, then just when I got this correct, we could have stopped. Okay. I hope you enjoyed this. Please like it, share with your friends, and subscribe the channel. Thank you for your time and doing math and CSIR crack the net. Okay. Goodbye. Tomorrow we'll again come with a new problem in abstract algebra.